Welcome to breadboarding. So this is the Breadboard PC, and in the previous video we added the two programmable interrupt controllers at the top here and our system data bus buffer, which is then feeding the data bus into these chips over here. So we added the real-time clock with its CMOS backup battery, programmable interval timer, various I/O decoding and address decoding, and then we've got the power on self-test port, which can hook up to our logic analyzer, and then the port B, which is used to switch the CPU down here between the default 14.3 MHz system clock and our turbo 25 MHz system clock. Got all the data buffers down here. We're plugged into our strip board bus rails here. So this is one of the enhancements I did over the version 1 PC. So this hopefully should give us slightly more reliable connections. And over here you'll see I've got a number of connectors here already plugged in here, which is what I use to plug in my 32-way logic analyzer, which is always a bit of a hassle to plug in a number of leads here. So this now means I can plug the logic analyzer in there a lot easier. Now in this video, what we're going to be doing is we're going to be taking the serial controller that we added a number of videos ago, and we're going to be moving it up onto this board here. We're going to be moving it up to here, and then we're also going to be putting the keyboard controller in here as well. And then some of the logic is going to go here and here for the bus integration. And then we'll also be adding the floppy disk controller and the hard disk controller on this board in future videos. So this is video 10 in the Breadboard PC 8088 version 2. This video we're going to be adding the PS2 keyboard, and I'll also be looking at making the BIOS video output available on the serial port. So this is our plan. We're sort of 2/3 of the way down making our basic floppy disk PC. So adding the PS2 keyboard controller here is what we're doing now. If you want to look at the version 1 videos, then video 27 and 28 covered the wiring in the keyboard controller and testing it. So there'll be a link for 27 at the top right hand corner here if you want to see that. Over the next number of weeks, we'll then be building out the CGA video controller, floppy disk controller, and trying to boot MS-DOS from floppy disk. We've been looking at what makes a micro IBM PC compatible, and all the things in green are things we've already done. We're not going to bother with a direct memory access, but we are now going to be doing the PC compatible keyboard. So once we've done the keyboard and then we do the video controller, then we should actually have a functioning PC, although we will need the floppy disk controller to be able to boot MS-DOS. This is our high-level design for our PC XT hybrid. So this is a step we're going to be doing now, the PS2 keyboard and mouse controller, and this came from the IBM PS2 era PCs. Now this is going to be the third video that I've done on installing PS2 keyboards. Now the first one I did was a number of years ago, back in 2023 I think. A Nanocomp 6809 Video 18 covers a lot of background on PC keyboards. There'll be a link at the top right hand corner of the screen. I went through in quite a lot of detail the various schematics across various versions of the PC and covered quite a lot of things in detail, which I won't go into now, but if you want to go into more detail about the background of this, there'll be a link to the Nanocomp Video 18 at the top here. So I reviewed the keyboard and the controller, so not only the controller on the motherboard, but also the hardware which is actually built into the keyboard. And we did that for the PC XT, 80, PS2 Model 80 and the Compact Despro 386. Covered the testing of the PS2 keyboard and USB keyboards with the appropriate adapter with the logic analyzer, looking at the various keyboard scan codes, so what is the actual information that comes back from the keyboard. And we also reviewed Sergey Kiselev's XI8088 BIOS keyboard source code as I was trying to understand how to interact with the keyboard, and I wrote a C-test program under 6809 for actually testing that out in this particular video. And a key thing also that I reminded myself by rewatching this video is that there are commands both for the keyboard controller and commands also to the keyboard. And when we're looking at the source code for this, we need to be very clear about whether we're sending the controller a command or whether it's a command which is being passed through to the keyboard. There are these two sets and it can be confusing. Now Ben Eater had done a number of videos on the low-level PS2 keyboard operation, and I'll include the link in the description below. So Ben goes through talking about the low-level signals and the clocks and things like that, and how the scan codes work in a great level of detail. So I'm not going to try and reproduce what Ben has done there. So I recommend if you really want to understand the low-level stuff, then have a look at Ben's videos there. So a bit of background on IBM PC keyboards. The initial IBM PC, which came out in 1981, is known as the Model 5150. That had an 83-key keyboard with a 5-pin DIN connector. So this is a larger connector than you would know with the PS2 keyboards. And this used the parallel port interface and a shift register to actually do the keyboard interface. And this is what the original keyboard looked like. This is an image from Wikipedia. And the PCXT, the Model 5160, came out, and I believe it used very similar or the same keyboard and used the same parallel port interface and shift register. Now, when the PC AT came out, the 5170, then there were two keyboard options. The first one was an 84-key enhanced keyboard, and then there was the 100 and 102-key keyboard, which probably looks more like a modern keyboard. So this is the enhanced 84 keyboard, and what you'll notice is that there are now the 4 keys at the top here, and in fact the escape key has moved from over here to here, and in fact the tilde key here, which was down here, has moved over here. So if we just go back, you'll notice there's only numlock and scroll lock there. We've got the tilde key there and escape key here, and then this 84 key version has got the tilde there, escape there, and these extra keys here. And then the enhanced 101, 102 key keyboard. The 102, I think, was for European keyboards. The 101 was the US. This is much closer to the style of keyboard that we would be familiar with today, and the layout really hasn't changed that much. There were Windows key and properties keys, I think, have been added in subsequent years, but the basic layout is pretty much the same. You can see the tilde keys there, and the escape key is now up there. And then when the IBM PS2 series came out, in particular the Model 80 we're looking at here, then this came out with the PS2 mini DIN pin standard here. This is the pin out of the PS2 keyboard port, and if you remember up to probably about 10 or 15 years ago, these were pretty standard, and these would be the purple and the green connectors on the back of the PC. So we're going to be using a standard PS2 keyboard with a 6-pin mini DIN plug socket, so you can still get these from Amazon for less than £20. I did a quick search. I wouldn't suggest you go for the mini ones. I would go for full-size keyboard, but you can see about £18 for a PS2 keyboard, and you can see there is the PS2 connector on the end there. Now, the Intel 8042 microcontroller was used in the PS2 and the Compact Desk Pro, but this was a microcontroller that was pre-programmed with the BIOS keyboard routines in there. Now, getting an Intel 8042 microcontroller with that keyboard BIOS is probably difficult to find these days, but there is a chip, the VIA VT82C42, which is a DIP keyboard controller, and you can get these for a few pounds, a few dollars on eBay. I've got about 4 of them, which I got doing about £3 and £5. And this is a compatible direct replacement for the Intel 80C42 BIOS version of the keyboard controller, fully implemented by hardware logic, so that it has very fast response capability for any command issued by the host. In addition to keyboard support, it also includes PS2 mouse support. So we're going to be using this 40-pin DIP chip. The pin out, again, I've reproduced here, is looking into the socket from the front, so you need to make sure that you get your orientation right when looking at the sockets and pins for these. An important point that I covered in the previous videos is if you're doing any testing on a keyboard, you need to include a 10K pull-up resistor on the clock and the data lines, because the keyboard has outputs which are open collector. So without the pull-up resistor, you won't get any voltage, and I thought I'd blown up some of my keyboards earlier and wasted a number of hours trying to find out why my keyboards weren't working, and this was the reason. And the other thing I discovered in earlier videos is that the VT82C42 is able to detect whether it's running in PS2 mode or PCAT mode, but it does need the mouse port wired up to detect that it's in PS2 mode, otherwise it will try and run in PCAT mode, in which case it won't talk to any PS2 keyboard. So let's take a look at the KiCad schematic and see what we're going to be doing in this video. I have uploaded all the KiCad schematics and all of the PLD configurations and information as of the previous video, so that's all been uploaded onto my GitHub site. So I will include the URL in the description below, and if you look at the previous video, I updated it to include the URL for the version 2 GitHub project. This is the Breadboard PC. Last time we did the programmable interrupt controllers over here and the real-time clock, CPUs down here. And this big block down here will be our CGA compatible video controller, which we'll be doing in subsequent weeks. So what we're going to be doing now is we need to move the serial port from the keypad and LED display board, which we did in a couple of videos earlier. The keyboard controller, we're going to be doing the VT8242. There's an 8 MHz crystal it needs, and then we have these open collector inverters, which we need to buffer the output, and we also have these pull-up resistors. Now, an important aspect of this is that we need to make sure that these feedback paths are included. So these feedback paths for the keyboard data, the keyboard clock, the mouse data, and the mouse clock are used by the controller to determine if it's running in PS2 mode or in PCAT mode. If we have a look at the data sheet, this section here includes how it actually determines whether it's in AT mode or PS2 mode. The registers and things, really, it's quite, you don't really need to get into that. Certainly if we're using the existing BIOS code, we don't need to worry about that. When I was doing the 6809 version, I did need to drill into that in a lot more detail, but we don't need to worry about that now. But this is the diagram that really we need to be worrying about. So this just shows the difference between the PCAT mode here and the PS2 mode here. So you'll see that because of the way how these feedback loops go into these signals here, then this is the way how the controller is able to determine if we're running in that mode or running in this mode. So in order to wire this up, what we're also going to need to do is to include the decoder that we included with the serial port previously. We're going to move this up onto this board on the right hand side here. So you'll notice here with the power rails here, we've got 1, 2, 3, 4 breadboards in the corner here. What I try and do in laying out the breadboards is to make sure that the chips and things are largely in the position that they're going to be, and it helps to work out where the wires are. You can see based on the number of wires going between the chips whether or not we might need to leave a bigger gap between the chips. Now, in addition to the decoder here, we're also going to need this data bus buffer. So this is similar to the database buffer that we did over here. In the version 1 Breadboard PC, I probably didn't put enough data bus buffering in, and so when the project got a bit larger, when we had 2 video controllers, then we probably were overloading the data bus a bit. So I'm putting in these data bus buffers on this one. Now we will be installing the floppy disk controller and the floppy disk controller port and another PLD necessary for that, plus also the IDE disk controller, its 646 bidirectional buffer latch, and another data buffer there, and then the IDE connector here and the various other signals here. So you're going to start by copying over the serial port, then we'll put in the PS2 keyboard and mouse controller, then wire up the PS2 mouse and keyboard connector. So what I'm going to do is I'm going to disconnect the board here because we're going to be putting quite a bit together on that board. What I'm going to do is just disconnect the Breadboard PC from the power supply here and move it off out of the way. And this is the serial connection into the PC here. We'll just disconnect that. So I'm just going to take this out. We'll put in our cutting pad there. Okay, so I've printed out all the chip labels and I've laid them all out, and I've actually stuck some of the chip labels on the various connectors. So that's the IDE drive connector and that's the floppy disk drive connector. Now when I was laying it out, I realised that I hadn't quite left enough room. I had this chip and this chip in the middle here, and I also had the oscillator, and there wasn't enough room really to fit that in. So what I've done is I've reworked it a little bit, and I'll show you the KiCad diagram in a minute. This is a connector for the keyboard and mouse that Peter had very kindly made for me a number of months ago, so I'm using that one now. So I'll just show you the changes I made to the KiCad diagram. Basically, the problem I had was this chip here originally in my diagram was here, and we also had the oscillator up there, and there just wasn't quite enough space. And also what I've done here is that this is a buffer that talks to the lower 8 bits of the IDE drive, and then this is a latch buffer, the 646 bidirectional buffer stroke latch. And what I've done is I've tried to line these up so that the pins are actually lining up straight for these two chips. So this will make it a lot easier to wire up on the board. And so it's one of the reasons why I prefer to do the schematics like this with the physical pin layouts, because you can actually lay out the schematic in a way that makes it easier to wire things up on the breadboards. So this chip has moved from here to here. This one's moved around a bit, and I've changed the order of the pins as well so they actually match to the IDE connector here a lot more easily. And then generally I've tried to space things out a bit, and you can sort of see where the busy parts of the board are, where there are more wires going between some of the chips. And then over here, because I moved this one over here, there was enough space to actually put the PS2 keyboard controller up here. And then by putting the buffer chip here and reorganizing this, I think it can make the layout a lot easier to wire up as well. So the logical aspect of it is exactly the same, but it's just a much easier physical layout, I hope, to wire all this up. So what I may very well do is plug in the chips for the later stage of the project as well, just because it just makes it a bit easier when laying things out to make sure that you haven't actually squashed something in where it won't fit. So what I'm going to do is to stick all these labels on the chips, plug all the chips in, and then I'm going to start wiring it up. And once we come back, then hopefully we'll have the PS2 keyboard and the serial port connected, and we'll be able to start testing it. First of all, we're going to plug in the ground and the 5-volt line. So there's a number of leads here that need to be tied to either 5 volts or to ground. We're also tying the unused inputs on the inverters to 5 volts as well. Another unused input there. Now the ground and 5 volt rails for the serial chip. That's the oscillator power. And a number of these need to be tied to ground or to 5 volts. The chip selects to 5 volts, the read and write enables to ground. Now we need to wire in the power for the buffer and the PLD here, and this other PLD. So now I need to wire up the PS2 sockets. This is a socket made by Peter. Just need to move those up by one because the pin 1 is not connected. So I've got different colours there for different signals. I'm using white for data, blue for the clock. Now we need to wire in the 8 MHz crystal for the PS2 keyboard mouse controller. We've got 2 capacitors and the crystal, and we're going to use another link there for the ground just so we can fit the capacitors in there easily. Now we need to wire up the mouse data. So that goes to pin 10 on the inverter there. I think I might have got one hole further down, so I need to change that in a bit. Then we need to wire in the data as well. Now I need to put in the capacitors and the pull-up resistors. So 2 capacitors there, and the pull-up resistors we're going to actually put down by the inverter outputs. Now we need to do the keyboard data and the keyboard clock. So white is the data and blue is the clock. Now we need to do the capacitors and the pull-up resistors for the keyboard data as well, and the clock. Now I need to wire in the 5 volts and the ground power supply for the PS2 keyboard and mouse. So now the P22 and P23 are the outputs for the clock and the data for the mouse. We connect those in. Test 0 is the feedback from the keyboard clock. The order I'm doing this is not optimal, obviously needed to move things around a bit. Then we need to make sure that the P10 and P11 feedback from the outputs here go back correctly. And this is how the keyboard controller works out if we're in PS2 mode or in AT mode. And then the test 1 feedback going from the output there. And then P26 and P27 are the outputs for the keyboard clock and keyboard data there. The order I was doing this is not optimal for fitting the wires in there. Now I need to hook up the serial port. I should mention that I missed out the A0 line, the read and write enables and the reset on the PS2 there, which I'll cover in a bit. Just wiring in the clocks there and the clock output into the receiver clock there. Now we're just going to wire up the USB serial converter. So there's 2 extra leads on there for the request to send and the think the data set ready. So just putting in some different color leads there for the various pins. Now wiring in the serial out and serial in to the receive and transmit. Now we need to wire in the various control signals. Now I did actually disable the data carrier detect and the DSO. I think I wired those to 5 volts. In fact, when I was testing things, I might need to look at that and whether I need to switch this back. So the PC DTR goes to the data carrier detect and the data set ready. It's clear to send to request to send. That's request to send going to clear to send, the yellow connection up there. Now we need to get the IO read and IO write wired in. So they're going to be going from that buffer there that we've created. And then we need to wire in the XA0 to XA2. And then there's the interrupt out there going to the edge of the board so we can plug in the interrupts later. Now we need to wire in the chip enables. So that's the serial chip select coming in from the PLD down the bottom right hand side there up to the chip select. Then we need to do the keyboard chip select from the PLD up to the keyboard controller. Now we need to do the positive reset, needs to go into the master reset signal on the serial controller there. Just put it underneath the address lines there. Now we're going to wire in the address A0 to A2 up to the PLD there, and also the output enable for the buffer. A0, A1 and A2, and then the output enable for the buffer. And then we're just going to put in the decoupling capacitors close to the ground connections for each of the chips. Now we need to wire in the address bus. So this is A0 to A7 is going to go over to our bus rails on the strip board. And then the data connections. So the X data is the internal buffered data bus here that we need to connect the serial port to the buffer and to the PS2 keyboard interface. Wiring all the data connections. Okay, so we've wired it all up now. So move this down here. We've got everything wired up, hopefully. So now we just need to put this into the main breadboard, and there's a few lines we need to hook up. So there's various IO select lines, the reset, does the I/O read and I/O write need to go in there, and the interrupt lines also need to go in here. So I'm just going to go off and wire that in and plug in the power, etc. When we come back, hopefully we'll be ready to switch it all on. Right, so here's the new board. We're going to be fitting it up top here somewhere. Plug in the power connector there. Because we're going to have the CGA card going to go down here, it's going to be about 4 across and 1 down the bottom. So hopefully that's in there okay. So I'm just going to wire everything in. I need to rearrange the reset and abort buttons down here, and rearrange this here. So when we come back, we'll have wired everything into the bus rails over here. We should be ready to switch on and give it a test. First, I'll need to wire in the interrupt lines from the interrupt controller down to the bus, and also then wire in the interrupt for the serial port and also for the PS2 keyboard and PS2 mouse. That's interrupt 12 for the mouse, interrupt 1 for the keyboard, and interrupt 4 for the serial port. Just wiring in the outputs from the interrupt controllers to the bus rails there. And we're just putting in some cables to take the interrupts from the PS2 chip over to the edge of the bus there. And just wire in those interrupts there. That's 4, 1 and 12. Now we need to wire in the I/O read and I/O write from the bus rails going into the PLD there, where they're then buffered to produce the X/I/O read and X/I/O write. That was the data transmit receive that tells the buffer which direction the data is going. Now we need to wire in the reset and the IO0XX and IO3XX. So those are the chip enable ranges for the IO ports. We've done those. We've done all of these control signals and the interrupts. Now we need to do the data bus and the address bus connections to the strip board there. Okay, so I've done a bit of testing. There were a few issues I had to fix. There was a link down here that had come undone when I moved the boards around and I hadn't put it back quite properly. I'd also missed out the reset line going to the PS2 keyboard controller, and there was the IO read and IO write also needed to be connected up from here to here. So those have all been put in. So everything's ready for testing now. So what I'm going to do first of all is to power it on and make sure the keypad's working. You can see here Nanocomp 8088 version 7, which is the version of the monitor we had last time. So if we just go into memory locations, that all appears to be working. And I've relocated the buttons here. So this is reset, and this is the abort, that if we are in a command like this, then that gets back to the monitor. So that seems to be working. Now what I'm going to do first of all is to just switch over to show the terminal program, and we're just going to do is to test saving an area of memory. So what I'm going to do is to save some of the monitor. So setting the extra segment at F000. Okay, so we've got the terminal set up here. So it's 9600 baud, no parity, 8 bits, and we've got request to send, clear to send, hardware handshaking. So I'm just going to send this little 4K chunk of the monitor first of all. Might take about 30-40 seconds to send, so we'll just check to see if we're getting the S record file on the real-time serial capture here. So that 4K of data in bytes has sent about 11,000 characters there. What I'm going to do is to try capturing the whole of the monitor area, and then we're going to look at it in the S record format just to check that there were no errors there. So I'm just going to run that now. Okay, so that's finished. It took just under 2 minutes to send 79K of data there. So what we'll just do now is to open this in our notepad. That appears to be okay. And if we save this as an SREC file, you'll see here that Notepad++ will actually interpret srecord files, and it will check that the checksum's okay. So you can see the right-hand column there is the checksum, and you can see here that we've got everywhere from F9000, which was the start of the EEPROM and BIOS, all the way down to the bottom here. That appears to be working okay, so I'm just going to try the loading now. What I've got is the post-beep test program that we used in some of the earlier videos, and I've got the srecord file for this, so we're just going to try and send that down and check to see if that works. We just need to set the extra segment to 6000, code segment to 6000, going to go into load, and back to here, and we're just going to go to send, and we can see here we've got the srecord file, so I'm just going to send that there. Okay, so that's finished, so we just now need to set the code segment to 6000, go 000. We've got post test, so we'll be capturing the power on self-test codes. I'll just get that running. Then we're going to get the beep test. And it finishes and it should show us the registers. So it looks like the download is working. We'll just check the power on self-test codes. If we look down the right-hand side here, we can see that we've got power on self-test codes going from FF all the way down to 01. That appears to be working. So the serial port's working. What I need to do now is to make the changes to the BIOS so we can output some of the basic BIOS power on self-test messages to the serial port so we can see what's going on. Okay, so this was a result of one of the comments. I'll look it up, see who it was. Thanks very much, whoever made the recommendation. So what I've done here is in the main BIOS, it outputs the power on self-test messages and various boot up messages to the video output using the TTY functions, so the teletype functions. What I've done here is I'm initializing the COM1 port, and what I've done is created a little routine here. This is the same initialization that we do in the monitor. So when we're sending data, this is save data in the monitor, it actually sets up the ports using these parameters. So all I've done is reproduce those parameters to make it nice and easy. And then in the video output, there is a particular interrupt. So the function 0e teletype output is what the BIOS uses for all its output. And all I'm doing here is when a byte is being sent for output, all I do is send that to COM1 first of all. So it's hard coded at the moment. There's no sort of flexibility to send it to a different COM port, but for the purpose of this, it's good enough. So we just need to build that. Okay, so I'm just going to program the BIOS and the EEPROM with the monitor in there, and then when we restart it, we'll check to see whether or not we can get any output from the BIOS. I've also plugged in the keyboard as well, so we'll also see if we get the keyboard output as well. Okay, so the EEPROM's been replaced and been programmed, so I'm just now going to power this on. The monitor is still version 7, but that's okay. So what we're going to do is going to type B for the BIOS, and that should boot the BIOS up. What I'm just going to do first of all is set everything up on the display here so we can actually see what's going on. So all I'm going to do is to press B to start the BIOS there. Okay, so we've actually got some output going to the terminal here. We can see here, we just have a look at here. So the non-volatile RAM checksum is invalid because we don't have a battery in there at the moment, so it's always going to fail when it first comes up. So if we hold down F1 when the BIOS starts up, then we should be able to go into the CMOS configuration. We can see that the main processor is a Harris-designed ATC8088, so this is now owned by Intersil. We don't have a Masco processor. The real-time clock time is not right because it'll probably all set to 1s. At the moment, the display adapter type is hard-coded on the keyboard controller as CGA. We don't have a mouse at the moment. It has detected COM1 as 03F8 because we do have COM1 installed. And it has also somehow detected there's a floppy disk there, although we don't have a floppy disk controller. And it's also detected 640k of RAM, which is what we have. And then boot failed. If we just press keyboard here, see if we actually get a retry. Yep, so the keyboard is working. What I'm just going to do now is to reboot it again and press F1, and we'll see whether we can get into the CMOS configuration. Okay, so rebooted, and now we're actually welcome to the BIOS setup utility. So if press H for help. So we're actually into the BIOS setup utility, so we can verify now that the serial output of the BIOS is working. I suspect it won't work very well for DOS, but it will work for anything that's just outputting text as if it's on a teletype. And what we'll do in the next video is we'll have a look at putting the battery in for the CMOS and actually setting all this up. And if we just check the power on self-test codes on the right-hand side here, we can see we've got going from 0.1 up to 0.9. I know that's where they're initializing the keyboard. And it goes all the way through searching for video BIOS and things like that. And then we get the 0.0 here means it's actually trying to boot the operating system. And then these codes here, the 0D ones, are basically additional information I've added to the floppy disk controller BIOS settings. As it's trying to boot off disk, then we get these extra messages. So we're actually seeing that the BIOS is actually going all the way up to trying to boot the operating system. We're not going to be able to get much further to boot MS-DOS until we've got our CGA video card and the floppy disk controller. So in the next video, I'll be starting to look at building the CGA video controller, and we're going to be focusing on the text mode initially, and then we'll look at all modes, including graphics, in a later video. And then we'll look at adding the floppy disk controller and booting MS-DOS from disk. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe, and if you can hit like as well if you found the content interesting, just helps to make the videos available to more people.